Hey guys, we're going to look at functions today, including the domain range and just some things about graphs. So first, how do we tell if something's a function? So the easiest way to say this is that your x doesn't repeat, but we also want to watch out that each element of our domain actually is mapped onto or has a y value. So if we look at this in these mappings right here below, we're looking at the x values really. Do any of these x values repeat? So on this one, no. So this would be a function. So every x value is mapped to only one y value is another way to say that. So this one is a function, yes. The next one, also a function. Each x value only has one y value. I don't care that this is repeated in the y's. 2 is mapped to b and 3 is mapped to b. What I don't want is 2 to be mapped to 2 different y values. So yes, this one is a function as well. Down here on C, this is what I was talking about. 1 is mapped to A, 2 is mapped to B. We have an element 3 in our domain that is not mapped to anyone. So this is not a function. This one right here on D, we see that 2 is mapped to B and C. So that means we would repeat 2. So we would have an ordered pair if we wrote it as 2 comma B and 2 comma C. 2 repeats. So this is not a function. Another way to tell this is if our graph passes what we call the vertical line test. If we draw a vertical line, and this one's easy because the y-axis is a vertical line, this can only touch one time. And this one actually touches 1, 2, 3 times. So this would not be a function. If we wrote those 3 ordered pairs, you would see that the x is 0, 0, 0, not a function. Here, if I draw vertical lines, if I do my vertical line test, every vertical line is only touching one time, which means x is only being used for one y value. So this one is a function. Next up, we're going to look at the idea of domain and range. So domain is all of our x's that we're going to use. Range is all the y's that we're going to use. We have discrete domains where we could list out every x value, and then we have what we call continuous domains and ranges, where you use every decimal, every fraction in between, so you would have to write them as an interval. This first one right here I could write as a discrete domain because I can literally list every number in the domain. So I'm just going to put D for domain, and I'm going to do the curly brackets and just list out all the x's used. 1, 2, 3. And range, I'm going to do the same thing, just R for range, and then I can literally list out all the y values that are being used. So we only list the ones that we're using, so A, B, and D. So those are domain and range. Domain, x, range, y. On here, b is a linear function. I know that. I could go to the graph on my calculator and look at it if I wanted to, but I do know it's linear, and I know it's a positive slope, so it's going to look something like this. So domain, x's, those are the values that go side to side. If I drew an x and a y axis on here, this would be my x-axis, this would be my y. It's going to go to the left forever and the right forever. So you can write that as all real numbers. You could write out the words. You can do the symbol for all real numbers like this. You can write negative infinity to positive infinity as an interval if you would like as well. Range, those are their y values. Those go up and down. So this is going to also go down forever and up forever, so also all real numbers. We're using every number there is. On C, we have an open circle, means not included, and a closed circle means included. And then it's continuous through the entire graph from there. So we want to look at the x values for our domain. Our domain, open circle, I'm going to use interval notation, so I'm going to use a soft bracket. And the furthest left this goes is at -5. But it doesn't actually touch -5 because of the open circle. And then we're going to go all the way to the right, and the furthest it goes to the right is a +5. And that's a closed circle, so we're going to use the hard bracket. Range, up and down. Now, the very bottom of this graph is at -2. The open circle is happening at -2, but I also have closed circles and a line right here on -2. So that means we're actually using and touching -2. So it's going to be a hard bracket. And then at the top, the very highest this graph goes is 2. So also hard bracket because it actually has dots on this line that are using the 2. D, domain, for this one, the furthest left it goes, we don't know because it's going to continue left forever. So soft bracket, negative infinity, it's going to go forever. And then to the right, the furthest it goes to the right is going to be 4, and that is a closed dot. So I'm going to put a hard bracket. Range, bottom, the lowest it goes is 0, hard bracket because a closed dot. And then the top it doesn't have a top. It's going to keep going up forever. So we do infinity. These next ones have a domain given. So what is the range that matches? So this is the graph 2x right here. I can graph this on my calculator. Like I said, I know it's linear, but I want to see what's happening from 0 to 10. And I probably think that that's probably going to be easiest if I go to my graph, put in 2x, and like we knew already, it's a line. But I only want from 0 to 10 right here. So 0, 0, I know that happens, but what happens at 10? So how high does it go up on the graph? Well, you can do Control-T on your calculator, and 0, my y value is 0. My x's, as I go, increasing just like I saw, but at 10, I get to 20. Now, I could have also just substituted that into the equation, but now I know for sure my range goes from 0 to 20. So you can use your calculator to help. We're going to save B for class. If you would like to try, you absolutely can. Now, example number 4. These are determining if we have restrictions that go with these graphs. I'm not going to do all of them on this video. We'll talk about a couple of them in class, but just a couple of notes. Linear, we know that's a straight line. There are no restrictions on the domain. Not at all. So we know already, because we've talked about linear, that the domain is all real numbers. A couple of notes about these other ones. Denominators cannot equal 0, so that's going to affect that one. Square roots. We know we have complex numbers or imaginary numbers if we take the square root of a negative. So the radicand, the thing that's underneath the radical or underneath the square root, we know that that needs to be 0 or positive numbers. So this cannot be negative, so make a note there. Natural log, we haven't talked much about, but what I will tell you is that the argument of a natural log, if you haven't seen it before, has to be a positive number. Again, here's the same thing, denominator can't equal 0, and then these other ones are related to the square root that I talked about. So let's look at maybe C. So I said that this needs to be 0 or bigger. So x's must be, or the radicand, I'm not going to put x, must be greater than or equal to 0. So we take out that piece, 3x minus 9, and we say this has to equal something greater than or equal to 0, and then we solve, and that'll give us our restriction on x. So I would add 9, so 3x is greater than or equal to 9, divide an x is greater than or equal to 3. So the only numbers we're allowed to use in this domain would be x's that are greater than or equal to 3. Any other numbers are going to get us a negative under that square root, and that would be an imaginary number. Let's look at E. E, the denominator cannot equal 0, so that's what's messing this one up. So the easiest way to do this is take your denominator and set it equal to 0. This one's a really easy one to factor, so I'm going to solve it that way, but you could definitely solve this in your calculator if you needed to by getting your solutions from the graph and solve either way. But I know that -2 times -1 multiplies to be a +2 and adds to be -3, so I'm just going to quickly factor. Each of these give us our solution, so x equals 2 and x equals 1. What this tells us is that if I put a 1 in that denominator down there, I'm going to get 0, and that's not allowed. So x cannot actually equal 1, and x cannot equal 2. So you can write it like this right here, or you can break it into pieces where we go -infinity until we get to 1, and we're going to go least to greatest, and then union 1 to 2, and then union 2 to infinity. So those would be all the x values that are allowed. This means that 1 and 2 can't be included. G is the last one on this set that I'm going to look at with you. There are two things that are happening. I know that the denominator cannot equal 0, so that one's an easy one to figure out. X just can't be 0. But then the numerator has a square root in it. So what we want to look at is the top, the radicand, 1 minus x squared, has to be greater than or equal to 0 right here. And I would look at my graph for this one. So we're going to go back to our graph. And we're going to add a new one of 1 minus the x squared, and we're going to look at that. I want this to be greater than 0, so that means that everything right here and above are what I'm looking at. So those x-intercepts are what I want to find out. So we go menu, analyze graph, and we're going to find our zeros. Over here on the left, I have -1, and then I do it again, and I find that over here on the right, I have a +1. So the piece, or the x's that are above that y or x-axis, are from -1 to 1, and we're allowed to include them. So we would say from -1 to 1 is where this is greater. So then you would want to put that together and say, I can go from -1 all the way to 0, but I can't include it, and then union, pick back up on the other side of 0 to 1. Okay, next up we have two functions that are given to us. This is a quadratic, x squared, and then this is a linear. Find each of the following. So the y-intercept of f, the x-intercepts of f, the maximum and minimum of f, and then the intersection of these two. So this is already in vertex form. So without even looking at a calculator, I can find that I have a vertex, that's what max and min is, at 3, -4. Now, if you're unsure, you can definitely put that in a calculator and see. Now, the a value is 1 and it's positive, so this is going to be a parabola that's opening up like this, concave up, which means this vertex has to be at a minimum. Now, we are going to look at this in a calculator so we can see all the other pieces. You don't have to do the conversion. So if you go to your calculator and you type in this equation and graph it, we will be able to see the picture. Okay, so I have it in here. Here's my parabola. Like I said, you could get this minimum right here by doing your analyzed graph. But let's go ahead and look at the y-intercept. So I'm going to go Control T to bring up a table. A y-intercept is where x is 0. So this table automatically tells me my y-intercept is at 0, 5. So I have that without much effort as well. X-intercepts, I can tell that there are 2 of them. So I'm going to do Control T again and get rid of this. And I'm going to do the same thing we've done before. So menu, analyze graph, number 6, and we're going to find the zeros. And we're going to go to the left side of that x-intercept right there, and then the right side, and that is at 1. So we have an x-intercept at 1, 0, and then we do the same thing to find the other one. So menu, 6, 0, go over to the left side of that, enter, right side of that, enter, that's at 5, 0. So we have 2 x-intercepts on that one. Now the intersection of these two, you want to graph the second one. So probably the easiest is to push tab and you get a second one here. And I'm going to type in my equation, x minus 5. And we know that's going to be linear. And now you can use analyze graph to find those intersections. So menu, 6, analyze graph, and you want to find the intersection, number 4. I have the left side, just like we do before, and then the right side where those intersect. So the intersection is at 2, -3, and then you can probably already tell where this one's going to intersect right here, but if you want to make sure that it's actually there, you can do analyze graph again. Remember, you can get things to move around by holding that middle button right here where the hand closes, and then you can scoot things over so you can see them better. But our other intersection is at that 5, 0, just like it looks like on there. Now, example 6 has these same 2 functions, but this time it says, find out where f of x is equal to g of x. Well, we actually just did this problem. Mathematically, what that looks like right here is this function equal to this function right here. But the intersections are where they are equal. But I don't want the whole intersection point. I'm solving for x. So the only part that's necessary is the x equals 2 and the x equals 5. You're finding the solution to that now. An inequality, this means that this is greater than g of x. So we want to see, where is f of x, our parabola, above the g of x? Well, I can tell by my picture. From this 2 this way, the parabola is above, and from this 5 this way, it's above. So that would basically be from 2 to -infinity and 5 to +infinity. This section between 2 and 5 is below. That's the part I don't want. So we would say the solution to greater than would be -infinity until I get to the 2, and then we're going to skip from 5 to +infinity. Now I want it to be greater, so all of these brackets are going to be soft. They're not going to be included. Example number 7 is a lot like what I just did, so you could go ahead and try that in your calculator. And here are your solutions to that. So hopefully you got that one right. If not, we can talk about it.